Hi guys, have your notes here for section 8.3 day 1. And before we get started, I'm going to pull up some previous notes just as a reminder of what we're doing when we set up an integral. So as a reminder, check out what appears to be like a purplish function here. Let's say that I wanted to find the area under the curve. So I've drawn 4 rectangles. We all know that that's not a good enough answer for the area under the curve. Imagine me putting in an infinite, let's squeeze in an infinite number of rectangles in there. So tiny that all I can do is draw a segment to represent each rectangle because it's super skinny. Oh, dang. So what we end up doing, skip. What we end up doing is we set up an integral, and in our integral, we put our function here. We put our function in terms of x here. This is a representation of all of the different heights of our rectangle. This represents each individual height of each individual rectangle, kind of one at a time. So this represents the height of a rectangle. This represents the width of a rectangle. Now remember, if these rectangles are super skinny and there's an infinite number of them, then their width kind of goes across the x-axis, and we call it the change in x. Super skinny, change in x, delta x, aka dx in an integral. This represents the super skinny width of each rectangle. And remember, what this does is it takes the height of each rectangle, multiplies it by the width of each rectangle. This guy calculates the area of each rectangle and adds them all together. This is our accumulator. What is it accumulating? It's accumulating areas of individual rectangles. So, also keep in mind, and I know a lot of you know this because a lot of you have been wanting to put units on your answers. When I ask, find the total area, and you're wanting to put units on your answers, which is fine. The units that you put on your answers, you always write square units. Why do you do that? Because you're finding area. You are taking a linear measurement. This is just a height. This is a single one-dimensional measurement. It's a height multiplied by a single one-dimensional measurement. That's its width. One-dimensional measurement by one-dimensional measurement gives us area, which is a two-dimensional measurement. That's what you've been doing. You've been obtaining two-dimensional measurements, square units. Remember, this accumulates. These two things right here represent the area of one rectangle. Let's jump to volume. So what I'm going to do before making this all complicated, what I'm going to do is give you the simplest function imaginable. Now, you're going to have to use your imagination with me for a minute. Because I used wrapping paper to represent the x and y axis, okay? And I tried as best I could to draw on the board the most simple function. So I've got a horizontal line. Some of you would try to say straight line, but if you've spent enough time around me, you'll know all lines are straight. This is a horizontal line, y equals 2. So what we're going to do is we're going to take this y equals 2, this horizontal line, and we're going to take this function. We're going to look at the area beneath it. We're going to look at this area right here, from the line to the x-axis. Ready? You got to use your imagination. Take this two-dimensional area, revolve it around your x-axis. What do you get? What shape do you get when you take this two-dimensional rectangle and you revolve it around the x-axis? I think you get a three-dimensional object that looks kind of like this. Okay, so again, you've got to pretend for just a minute that these wrapping paper rolls are super thin. They're just an X and a Y axis. And wrapped around this x-axis is a cylinder. It is a three-dimensional solid object. Now, this might not have been such a great representation because you and I both know that the center of a paper towel roll is not solid. Use your imagination. What if it were? Then our result would be a completely solid cylinder. Completely solid. Find the volume of that cylinder. So now it's up to us to find the volume of a completely solid cylinder. How do you find volume? Well, some of you are going to refer back to volume formulas from geometry. This is the concept of volume. What is the concept of volume? The concept of volume says, take a look at what shape the base of your figure is. What shape is the base of my figure? Well, the base of my figure has a shape of a two-dimensional circle. And you all know how to find area of a two-dimensional circle. Area. But what's volume? Volume is just repeated area over and over and over again. So it's, okay, take this base and now stack it on top of each other, stack it on top of each other, stack it, stack it, stack it, stack it, stack it, stack it, stack it. How many times do you have to stack it? So what we're going to do is we're going to take the area of a base and we're going to repeat it and we're going to stack it on top of each other. What we get is sort of like a stack of paper plates. Okay, my stack's not quite tall enough because it's supposed to be this tall, but I didn't have enough paper plates. So what I get is I get a circle. I get the area of a two-dimensional circle over and over and over and over and over and over and over again. Because I'm taking the area, two-dimensional, times the thickness of the paper plate. And we take this thickness and we repeat the thickness over and over and over and over again. We take the thickness and we repeat the thickness over and over and over and over again. That's how I get the stack of paper plates. Okay? Now, again, back to your imagination. I'm showing you volume as with a base and stacking because that's what makes sense to you. But remember the solid that we saw by revolving this around the x-axis? It went like this. So our plates are actually stacked up against each other, as if you just got finished washing a bunch of plates and you put them standing in a drying rack to dry. That's how our plates are, okay? So that's kind of what you need to imagine. That's what we're getting ready to do, is we're going to look at plate after plate after plate after plate after plate after plate all the way through. Let's take the area of one plate and then let's start accumulating it. Okay, so back to your notes. 8-3 day 1. And of course, the function that we're going to be looking at to start off with isn't the most simple function. We're not looking at a horizontal line. We're looking at, still kind of simple, but we're looking at y equals x squared. So let's check out y equals x squared And we're going to start at x equals 0, and you know it's half of a parabola. We're going to stop it when x is 2. Let's look at the area underneath it. So check out just this area. Okay? That area is what I want you to imagine, this yellow area. I want you to imagine this yellow area being revolved around the x-axis, and what shape would it make? Well, obviously, it would make all of this. And you know how this is like the outer edge up on top? Well, this would be the outer edge all the way around, so this would kind of be mirrored down here as well. Okay, now you can see that this makes a circular shape, and now I want you to imagine taking a knife and slicing through this as if it were like a loaf of bread. So start slicing, start slicing, start slicing, start slicing, start slicing. If you were super hungry, I think you would want to wait until we got to the biggest slice down here. And this is the slice that you would choose. If you weren't super hungry or not really a bread person, you might take one of these smaller slices here at the beginning. Okay? But my point is, each slice has a different size. Each slice, in this case, is a circle. Each slice, so it's kind of like stacking a bunch of plates in a drying rack. My plates get bigger every single time. Big idea. Here's what we want to do. Let's write a representation of the area of one of those plates. Not the actual area, because the area of each plate changes as we progress through these x values. But let's write a representation of the area of one plate. That's a two-dimensional measurement, right? Let's write a representation of the area. That's a two-dimensional measurement. And then let's take each area, let's take the area of each plate and let's multiply it by its thickness. Now, if I stack these right next to each other over and over and over and over and over again, how thick is the paper plate? Well, I think you're going to tell me that the plate is super thin. Yes, it is. And it's going along my x-axis. So that would be dx. Okay? So here's what we're going to do. We're going to take the area. We're going to represent the area of one plate. That's a two-dimensional measurement. We're going to multiply it by the thickness of the plate. And since my plates are stacked this way, that's going to be dx. And we're going to put it in an integral. So the integral will do the areas of each plate. As the plates get bigger, they're going to do each area times the thickness, add all of those areas together so that we end up getting volume of a crazy looking shape. Okay, so if you want to pause that and jot that down, these are kind of like the steps that we're going to go through. And I'm not a huge person like let's memorize steps, but if you try to do we're going to get some hard problems. And just knowing these steps is not going to ensure that you have the right setup. You're still going to have to use your brain. But if I can get you to think through this process each time, you'll do a better job. Okay, let's try one that has a different shape. And what you're going to have to do is, this is going to be all you from start to finish. We're going to do, this is what we're rotating our area around. You're going to have to draw the curve y equals the square root of x. You're going to have to know what that looks like. Notice I've shaded the area between the curve and the x-axis. So this two-dimensional yellow area is what we're going to send around the x-axis. Oh, and it says go from 0 to 1. So I stopped us here at x equals 1, and it's always good to write your ordered pairs. So we know that when x is 1, y is going to be 1 also. All right, so let's revolve it around. Here's what its mirror image would look like on the underside. Kind of like that. And now all of this is filled. It's solid. It's completely solid. Let's find the volume of that solid, okay? So it's round. Let's find its volume. So what we're going to do is we're going to imagine cutting through the solid. And each time I cut through, we're going to look at a cross section. Again, back to geometry, a geometry term. Each cross section, if this were a loaf of bread, each slice of bread would be a circle. Let's investigate the area of each red circle that I could draw. I'll draw a few, but we really don't need to draw a lot each time. But I'll draw a few just to kind of get you going on this problem. So there's a few circles. You can see that each circle gets bigger and bigger as I progress through. So the area of the circle is pi r squared. Now, how do we customize that for this particular problem? Well, for this particular problem, each circle, again, you're looking at a circle like this, right? It's super thin. Well, what does it look like when I take it out and look at it? It's a two-dimensional circle. Look at its radius. The radius of each circle extends from the center of the circle to the outer edge. From the center to the outer edge. From the center to the outer edge. From the center to the outer edge. So I'll draw one. Here is one representation of a radius of a circle. What kind of measurement is that? It's a vertical measurement. It goes from our x-axis to the function. It's a vertical measurement. I like to call it y. It's not just any y. It's not just any vertical measurement. It's a special vertical measurement because it starts on the x-axis and it goes to our function. So I'm not just going to call it any y value. I'm going to call it the y value. It's not just any vertical measurement. It is the true y that represents the distance from when y is 0 till it reaches our function. It is the y value. So I can say now my area of my circle is pi times y squared. Now, that is a representation of one plate's area. I'm going to need volume, so I'm going to need to multiply the area of one plate times the thickness of the plate. Well, how thick are these plates? Yes, this thick, this thick, this thick, this thick, that's dx. So I'm going to do pi times y squared times the thickness of each plate, which is dx. And I want to accumulate those over and over and over again. So I'm going to do this. Now, where does our stack of plates start? Our stack of plates starts here, and we start stacking them and stacking them and stacking them and stacking them. Where does our stack stop? Our stack stops when x is 1. We start the stack when x is 0. We stop the stack when x is 1, 0, 1, slight problem. So it's a good representation. This represents the area of a plate. This represents the thickness of a plate. We take a two-dimensional area, two-dimensional measurement, times a one-dimensional measurement, and I get a three-dimensional measurement. I'm going to get volume out of this. The only problem is these are x's. This is an x. This needs to be in terms of x. Yes, it's a y measurement. But what is the y measurement? The y measurement is the square root of x. So the only thing wrong with the integral that we just wrote is, yep, this is a y measurement, but it has to be in terms of x. So I have to replace this with, what is the actual y function? Let's put the actual y function right there. So my radius is actually the square root of x, right? Thus, my area is actually pi times my y function, but in terms of x. We looked at an area equation. We determined what the radius was. We're going to have to get our radius in terms of the proper variable to set up our integral. So this does, remember, this is a representation of the area of one circle. This is the thickness of the circle. So just these pieces right here, this is going to get the volume of every single plate. And this is going to add those volumes together, starting when x is 0 and accumulating all the way through until x is 1. Now, whether you're using your calculator on this or not, you could always pull your constant out. Pull my constant out. 0 to 1, x dx. And when I evaluate just the integral on my calculator, I get 1/2. Throw your pi back on, and you get pi over 2. Okay, so what I'm going to do for the next two problems is I'm going to start, now that you know, you saw the problem that we had right here when I put a y here. You saw the problem that we had. So from now on, I'm going to write my area formula. I'm going to get it in terms of whatever I need to get it in before I create my integral, so I don't have to backtrack and erase and change. But I kind of wanted to show you the wrong way first so that you'd be able to recognize when you've got it set up incorrectly. Alrighty, next one. We have a cubic function, and this time, so you should be able to draw that. You should be able to know that when y is 8, x is 2. See, y is 8. So here's what we're supposed to shade. We have to figure out what to shade first before sending it around an axis. So it says it's got boundaries. This is a boundary. This is a boundary. Y equals 8 is a boundary. That's a horizontal line. Y equals 8 is a boundary. And x equals 0 is a boundary. So I'm going to shade this area so function, horizontal line, axis, x equals 0. This is the region that we're going to revolve This time, let's revolve it around the y-axis. So imagine taking this shape and we're going to spin it around the y-axis. So let's kind of draw what it would look like. Let's draw kind of the mirror image over here. I need you to imagine that that is a completely solid object. Okay? Now, slice it. This time, you're going to slice it this way. Okay? Because, check this out. When I visualize me revolving it, watch the circle that my hand makes. My hand makes a circle like this. That means my plate would look like this way, stacked on top of each other. Now my plates are stacked on top of each other. Draw a circle or two to represent one of your plates. So this time, plates are stacked on top of each other. They're getting bigger and bigger and bigger and bigger. Let's check out the area of a plate. Well, the area of a plate is pi r squared. Focus on one individual radius. For each circle, the radius would go from the y-axis to the edge of the function. So I've got area of a plate is pi r squared. Let's talk about what r is. This time, r is a horizontal measurement. What do you all like to call horizontal measurements? You like to call them x. But it's not just any horizontal measurement. It's not just a horizontal measurement out here or back here. It's the horizontal measurement that goes from the axis to the function. It's not just any x value. It's the x value. My radius is the true x because it starts on the axis and goes to the function. So my area is going to be pi times x squared. So what we need to do is we need to set up an integral that represents the area of each plate, the thickness of the plate. Oh, now hang on. Thickness is different this time. See how the plates are stacked? This time the thickness of each plate goes up the y-axis. Delta y, delta y, delta y. So we're going to need area, we're going to need delta y, and then we're going to need where do our plates start? Where do our plates stop? So I think you can tell that our integral, our plates are going to start at y equals 0. Our plates are going to stop at y equals 8. The thickness of each plate is going to be dy. So this needs to be the area representation of one plate, but my variable has to be y. These are y's. This is y. This has to be in terms of y, and right now my area isn't. No big deal. Just go back up, go up to your function, do a quick solve for y. X equals the cube root of y. So area equals pi times the cube root of y squared. I could also write this as y to the, let's see, squaring it, cube root 2/3 power. And you can evaluate like this, or you can pull the constant out in the front. You'll get a cleaner answer if you do that. You can pull the constant out, go from 0 to 8, y to the 2/3 dy. When you type this part in your calculator, just pretend they're x's, just to get your calculator to tell you the answer you want. And then don't forget to throw your pi back on the end. And I get a nice clean answer of 96 pi over 5. Okay, last one. We've got parabola, y equals 0, and x equals 2. Y equals 0, x equals 2. Y equals 0. This is the area that we're looking at. Make sure you've got your boundaries good. That's the area that we're looking at. Only this time, ooh, tricky. We're not revolving it around the x-axis. We're not even revolving it around the y-axis. We're revolving it around the vertical line x equals 2. So we're going like this. So here's what it's going to look like on the other side. Sort of. Same concept. We're still looking, so we're doing this, right? Do you see the shape? Do you see the circle that I'm making? So it's going to be plates stacked like this. I'm revolving this way, plates stack on top of each other. These circles that I'm making with my hand are going to stack on top of each other this way. I'm going to draw a couple of them. Let's look at a radius. The radius goes from here to here. You see that? For each circle, it doesn't matter where I draw it. Doesn't matter where I draw the circle, the radius goes from the center to the outer edge. From the center to the outer edge. From the center to the outer edge. All right, it's tricky. Ready? What do you want to call it? It is a horizontal measurement. What would you like to call it? I'd like to call it an x value. I would like to call the radius an x value because it's a horizontal measurement. But wait, is it the x value? So the true x value, and what do I mean by true x value? Okay, watch. Let's say that I look at a point. Let's say I look at this point right here. This is the point 2, 4. This is the point 2, 4. Ready? What's 2? 2 is the distance you travel from the y-axis. It's the distance that you go right. It's the x in my ordered pair. It's the distance from here to here. What's 4? Well, 4 is the distance. 4 is a y value. It's the distance from the axis to the point. Right? This is the x value. This is the y value. Why? Because they start on an axis. This is a horizontal measurement that's just out there somewhere. It doesn't touch the y-axis. It's just kind of a random sort of x value. What's the x value? Watch. The x would look like this. I'm going to draw it for you. The x would go from here to here. The x. This is not the x. It's some other x. And it changes. When this is the x, my radius is a pretty good sized radius. When the x gets really big, my radius is a pretty small radius. What does it depend on? Well, how far is it from this blue point from the y-axis? How far is it all the way, keep going, keep going, keep going. How far is it all the way to there? 2. What do I want? R. What do I not want? The x. If you didn't get it, rewind it. So my radius is going to be represented by the whole thing minus the part that I don't want. The whole thing, which is 2, minus the part that I don't want. So my area representation for each circle is going to be pi times this squared. Let's see how that works out for us. Ready? This is the area representation for each circle. Now, how do our plates go? How are they stacked? Our plates are stacked on top of each other this way. Uh-oh. Where do our plates start? 0. Where does our stack of plates stop? 4. We start at y equals 0. We're stacking them in a y direction. Our stack stops at 4. So since my plates are stacked like that, I'm going to go from 0 to 4. How thick is each plate? dy. What do I write for the area representation? Not that. No problem. Just get this in terms of y. So my area is really pi times 2 minus radical y squared. These are y's. This expression is in terms of y. This is dy. It matches. This is the area of each plate. This is the thickness of each plate. Here's where our plates stop. Here's where our plates start. Here's where our plates stop. Before you do an integral, you might want to pull the pi out. And I get 8 pi over 3. Okay, sorry this was so long. Good luck. Step out of that comfort zone. Ask me questions if you get stuck.